Welcome to this demonstration of a reconfigurable 5G WAGF architecture, developed as part of the 6Green and 6G SNS joint initiative. In this video, we present the contribution of the Technical University of Madrid to the 6Green project. The implemented solution centers on an Access Gateway Function, or AGF, deployed on a standard x86 platform equipped with Netronome SmartN ICs. The data plane is accelerated using eBPF and XDP offloading, enabling high-performance packet processing at the edge. The AGF integrates with a 5G core using free 5GC and supports two critical capabilities: user and session migration between gateways and traffic consolidation for energy savings. The system architecture involves two AGF instances, AGF1 and AGF2, each handling user traffic independently. A central controller orchestrates user migration decisions and manages DHCP-based IP reconfiguration. The 5G core, provided by free 5GC, handles authentication, session management, and user plane functions. User equipment devices, UE1 and UE2, can be dynamically reassigned from one AGF to another without service interruption. The migration mechanism relies on DHCP-based network-initiated updates. When the controller decides to migrate a user, it sends a DHCP force renew message to the affected client. This forces the device to request a new IP address, which is then assigned within the target AGF subnet. This process enables seamless handover without any user-side configuration or disruption. Once the migration is triggered, the controller determines the optimal target AGF for the user. The selected user is then seamlessly moved from the source gateway to the destination one, while maintaining service continuity. As a result, traffic can be consolidated into a single AGF, allowing the idle gateway to be switched off. This approach improves overall resource efficiency and reduces energy consumption. Regarding results, the system demonstrates significant energy savings by consolidating all active traffic onto a single AGF and powering down idle gateways. Measurements show that power consumption remains nearly constant regardless of traffic load, confirming that the bottleneck lies in the gateway's idle power draw rather than its active processing. This validates the energy efficiency of our consolidation approach. In conclusion, the implemented AGF supports full migration using DHCP force renew for network-initiated IP reassignment. Traffic consolidation onto a single active AGF enables meaningful energy savings. The solution is deployable on commodity hardware with smart NIC acceleration, making it a viable and efficient approach for future 5G access network deployments. Now let us walk through the demo execution. The process involves 7 steps. First, we start the 5G core using free 5GC. Second, we launch both AGF instances and connect them to the core. Third, we connect the user equipment. UE1 connects through AGF1 and UE2 through AGF2. Fourth, we start the central controller and its DHCP server. Fifth, we trigger a handover from the controller UI by selecting UE1 and assigning it a new target AGF. Sixth, we observe the DHCP force renew messages appearing in the console logs as UE1 receives its new IP address. And seventh, we verify the migration through Wireshark packet captures and HTTP request logs, confirming successful connectivity through the new gateway. We are now entering the live demonstration. You can see multiple terminal windows open across the monitors, each corresponding to a different system component. We begin by starting the free 5GC 5G core. We then configure the subscriber data through the free 5GC portal, adding the necessary subscription entries for our user equipment. With the 5G core running and both users created, we now start the controller. You can observe that at this moment no user appears to be connected to the AGFs, since these have not been started yet. Then each AGF connects to the core and registers its network functions. The terminal logs confirm successful attachment and session establishment for both AGFs. At this stage, UE1 and UE2 are already connected, each attached to a different access gateway function. The logs show the attach procedure completing successfully, with IP addresses assigned from each AGF subnet. UE1 is currently communicating through AGF1, while UE2 is connected through AGF2. Before triggering the handover, we verify end-to-end connectivity. Both UE1 and UE2 send traffic towards the 5G core, confirming that the network is operating correctly. Packet captures using Wireshark show the exchange of GTP and ICMP traffic, validating the correct data plane behavior through each access gateway function. Once connectivity is confirmed, DHCP clients are started on both user devices. This step prepares the system for network-initiated IP reassignment during the migration process. We now proceed to trigger the handover. From the controller interface, UE1 is selected and AGF2 is defined as the target gateway. Once confirmed, the controller initiates the migration process by sending a DHCP FOSS-renew message to the device. Wireshark captures confirm the packet exchange during the handover, showing both control and data plane activity throughout the process. Immediately after the migration, connectivity is maintained. Traffic from UE1 continues without interruption, now flowing through AGF2 with the updated IP address. After the handover, UE1 is assigned a new IP address within the AGF2 subnet, as shown in the terminal. Despite the IP reassignment, connectivity is fully maintained. UE1 continues sending traffic without interruption, demonstrating a seamless migration. Similarly, UE2 can successfully communicate back with UE1, validating bidirectional connectivity across the updated network path. Thank you for your attention.